So let's go ahead and review the simple harmonic oscillator and look at all the details of what happens through. Basically, we're going to do half an oscillation, but if you do half, then you'll know what happens during the full oscillation. So we have a spring that's compressed at what we'll call negative X max. There's a force to the right, which is going to increase its speed, and it's going to decrease its displacement because it's going back to zero. So then it gets here, and then it continues because it has its max velocity here. Its acceleration is zero because at equilibrium there's no net force. And then as it moves along here, the force starts to act in the other direction, the negative direction, which slows it down to reach this point where its potential energy is a maximum, its position plus x is at a maximum, and its velocity is at zero, and the acceleration is at the highest point because F equals kx. So the net force is the largest. So let's go ahead and look at all of this in a graph. If we start here, our X max position initially is negative X max. So we're going to start down here. And what happens to that position? Well, it's traveling back to zero. It's curved because it's accelerating. It reaches equilibrium, and then the slope decreases, which means it's slowing down. Now, if we continued, then it would be this on the return trip. What about the velocity? Well, the velocity at the left end is stopped. It's all potential energy, the kinetic energy is zero. So what does it start to do? It starts to speed up, but its rate of change, the slope of the line, the acceleration is at a maximum here, and then that decreases until it gets to here where it's at V max. Then it begins to slow down as it gets to the other end over here where V eventually becomes zero. So what happens if we watch this continuing? Then it would come back and this pattern would repeat. And finally, if we look at this for the acceleration is maximum when the spring is at maximum compression. Why? F equals kx. X is at a maximum, so the net force is at a maximum, so A is at a maximum. But that acceleration decreases because the x is decreasing. It reaches the central position where it's at equilibrium. So there's no net force, so the acceleration is zero, and this is the point where v is at a maximum. Then the acceleration starts to increase negatively, which is slowing down the mass until it gets to the maximum value when it's all the way out at the other end and it stops, and then this pattern continues along with the same curve. Okay, let's take a minute to look at the energy in a simple harmonic oscillator. So we've done this a bunch now. We've got the mass that's oscillating back and forth on the spring. And if we look at it at this point right here, what kind of energy does it have? Well, at this point, it's at its maximum negative position, so it's stopped, which means that if we look at the energy total, that's going to be U plus K. And what is the kinetic energy once it's stopped? That's zero. So the total energy is going to equal U max, which is going to be 1/2 kx max squared. So that's the total energy. But we could also do it here, which would be E total, the total amount of energy, would be U plus K. But at this point, this spring is at equilibrium. So it's not stretched. So U is zero. And at this point, the E total would be equal to 1/2 mv max at that point squared. And obviously out here, this would be the reverse of the first situation. That would be U plus K, and we're back out at the maximum. It's stopped, so that would be zero. Well, what would that look like if we graphed it? Well, we know that when we're right here, that the kinetic energy at the end is 0. And what happens to that kinetic energy? Well, that kinetic energy increases, and it increases until it reaches a maximum at x equals 0, at equilibrium. And then on the other side, what does it do? It starts to decrease until it stops. Well, the whole time that's happening, the potential energy, which is at a maximum here, decreases until it reaches this point, and then it starts to increase until it gets to the other side at its maximum value. Well, what if we were to graph the total? Well, at any point, here is our kinetic energy graph, and here's our potential energy graph. If we add these together in a line, we get the total energy. And if we do it here, we get the total energy. At any point, this is going to be the same value, telling us, as long as there's no friction, that the total energy remains the same. This is more review than anything. We did this back when we did the forces unit, but just as a refresher, if we have a spring that's hanging here like this with no weights on it, and then we add a weight, we can figure out the spring constant from F equals kx. And what is the force? Well, that's going to be the weight on the spring, or mg. So that's a way that we can end up solving for x. But one thing that I want to point out is that they'll often say something like this, that the mass is brought down some distance, we'll call it x1, and then released. Well, if it's released from this point x1, it's going to start to oscillate with that same value x1, where this is our equilibrium. In other words, this is the original equilibrium, but by hanging a mass at rest here, we've created a new equilibrium, and whatever height you pull it down, that becomes the new x max, or we could say that becomes A, the amplitude. Okay, this is solving for springs in series, and what that means, if you've done electricity in a previous lesson, usually in an introductory physics course, series just means one after the other, kind of like the World Series. They go in order. So let's say we have two different springs. K1 is greater than K2, so this is a high spring constant. So we apply a force that is going to act on both of these springs. So the force is uniform throughout. Well, if that's the case, the one with the higher spring constant is going to be harder to stretch. So that one's only going to stretch a little bit, and the lower spring constant is going to stretch a bunch. So we can say that the total x total, is going to equal x1 plus x2. And if we look at this with F equals kx, then we can rearrange and say x is equal to F over k. So all we have to do at this point is add them up. So if we say x is equal to x1 plus x2, then we can rearrange and say F over k is equal to F over k1 plus F over k2. And this k, we call this k effective. In other words, this is the effective spring constant of the two combined. Well, these forces, there's only one force, so we have an F on each side, so those F's will cancel out. So for springs in series, the formula is 1 over k effective is equal to 1 over k1 plus 1 over k2. So we can say that k effective, no matter what these values are, because these are adding reciprocals, k effective will be less than k1, and k effective also has to be equal to or less than k2. So what we're effectively doing is lowering k by putting two springs in series. So what would happen if we took these springs and we hung them in series. So we took one like that, and we took one like that, and we added a mass. So now we have K1 and K2. What would happen to the period if we put these in series compared to individually? If we pull this down in amplitude, remember what we just said, whatever that amplitude we pull it down, that will be the new amplitude it oscillates at. Well, let's look at our formula. What have we changed? Well, we have made K get lower. We have taken K1 and K2, added the reciprocals, and we get a lower K, K effective. So what happens? The period must go up. What about springs in parallel? So if we have two springs and we put a light rod in between them and then pull on them with one force, what's going to happen? Well, these springs are going to stretch out the same amount, but the forces are not going to be the same. If K1 is greater than K2, the force here is going to be greater than the force here. So, but there's only one force total. So this total force is the sum of force 1 and force 2. So we can say that the force total is going to be equal to F1 plus F2. And we know that because they've stretched out the same amount, that x that they've stretched out, that's the same. The total x is the same as x2 is the same as x1. It's all one thing. So we can sub in for F total and put in kx, and that k is going to be our effective k. That's going to be equal to, and that's going to be our total x. Then that's going to be k1 x1 plus k2 x2. But x total, x1, and x2 are all the same thing, so those are all going to cancel out. So this one's pretty easy. Four springs in parallel, the effective k is equal to k1 plus k2. Here's a common question that gets asked. We have a bunch of different organizations of springs, but the K is all the same. So the K's are the same. And the question is, if we set these into motion, which one is going to have the greatest period? So if you look at it this way, we start out with a spring that is in just a single spring at K. So its K is just K. But for the springs in parallel, this is a little more complicated because our formula is 1 over K effective, which is equal to 1 over K1 plus 1 over K2. But in this case, these K's are the same. So we can say 1 over K plus 1 over K is 2 over K. And that's equal to 1 over K effective. And if we rearrange and solve, cross multiply, solve for K effective is equal to K over 2. In other words, half of K. So this one is K, this is K over 2. And then for K effective of them in parallel, that's just K1 plus K2. These are the same, so K effective ends up becoming 2K. So which one of these situations is going to produce the greatest period? Well, the one with the greatest period is going to be the one with the lowest K. Well, which one has the lowest K? That's going to be K over 2. So the spring that's going to take the longest time to go back and forth is going to be this one.